All right, so we're going to start out looking at section 7.5. We've looked at what we call the fundamental identities. Those cover the reciprocal. So like when you flip the sign, you get the cosecant. They cover the Pythagorean identities, like sine squared plus cosine squared equals 1. And they cover the tangent and cotangent identities, like tangent is sine over cosine, cotangent, cosine over sine. What we're going to look at now is a few other groups of identities, starting with what's called the sum and difference. So I just want to take a look at those two ideas. The sine of x plus 3 versus the sine of x plus the sine of 3. Just think about these two problems as a transformation problem. A transformation of sine x. What would this one be doing? It would be shifting it left 3. What would this one be doing?
It would be increasing up by 3.
It would be shifting it up the sine of 3, whatever that is. So, is that the same transformation? No. So, they wouldn't look the same at all if you graph them. And the idea here is you can't just distribute sine to two things inside the argument. That doesn't work at all. It's kind of like if I said the square root of 9 plus 4, and you said, oh, well, that just equals the square root of 9 plus the square root of 4. It's like you tried to distribute the square root function to the 9 and 4. Well, this is the square root of 13. This is 3 plus 2. And 5 is not the square root of 13. So you can't distribute functions to what's inside the argument. That doesn't work. So the question is, what does work? How can we take something that has addition inside, we're going to look at sines, cosines, and tangents, and turn it into something that doesn't have addition or subtraction? This is what we would call a sine of a sum. So there's a sine sum formula. There's also a sine difference. There's a cosine sum and difference and a tangent sum and difference. Now, once you know one of the identities, you can kind of figure out the other ones based on the first one. To prove this first one, I've done it before, but it's off the top of my head, I don't remember how to do it. Second, it takes a little while. So the amount of time it takes to prove it isn't really worth for what we're doing. So the first formula I'm going to give you, which is for the cosine of a difference, we're not going to prove. Okay, but we will prove some other ones after.
You just understand that it works.
Yeah, and this does work, and it can be proven. It's just a little bit more than we really want to spend for the value you get out of proving it right now. So these two, alpha and beta, would represent angles, like 30 degrees minus 10 degrees, or something like that. And if you have the cosine of a difference, this is what it turns into. And everything with sines and cosines pretty much turns into something like this. It always turns into 4 things. Sometimes the cosines are next to each other and the sines are next to each other and there's a plus between them. Sometimes it's cosines and sines with a minus between them. That's a little bit different from them. Sometimes the sines and cosines are mixed. Like you have a cosine times a sine and then a cosine times a sine. In this case, they're not mixed. The cosines are grouped together on the left of the plus sign, and the sines are grouped together on the right. And what I usually refer to these things as is first and second. My first angle and my second angle. So cosine of the first times cosine of the second, plus sine of the first, sine of the second. That's the pattern. And again, the proof of it is on page 409, which is online. Yeah.
Is multiplication between the cosine and sine.
Yes, that is multiplication.
Yeah, I guess.
Now, generally, this formula is used if you want to do something arithmetic-wise with it. If you want to calculate a trig function that's a multiple of 15. So we studied unit circle trig, and when we did that, we did multiples of 30 and 45. But I showed you on the diagram, if you draw all your 30s and 45s, it basically looks something like this. There was like a little bit of a gap in each quadrant near the axes. The 30s, the 45s, and the 60s are all kind of in the middle. What we didn't have were the 15s, like 15, 75, 105. That would be 15 before, so that's 165, 195, and so on. If we can figure out how to do the 15s, then we'll be able to do every angle that's equally spaced 15 degrees apart on the unit circle. And that's one thing that the summing difference formulas do. They help you to figure out the 15s. I'm going to show you how. So let's find the cosine of 15. Now, if you do it on the calculator and you type it in, you're going to get a decimal. That is not what I want. I don't want 0.9659. I want the exact answer. So the way to do this with the formula I just showed you is to try to think of two angles that you can subtract, and it comes out to 15. But the two angles that you use have to be multiples of 30 and 45. So you can't do like 20 minus 5. That wouldn't help. But can anybody think of two numbers you can subtract?
60 and 45?
Yep, you could do 60 and 45. Was anybody thinking of anything else?
30 minus 15.
15 is not a... So we want multiples of 30 and 45.
Yeah.
15 isn't a multiple of 30.
Oh, 90 and 90.
30 is a multiple of 15.
Oh, yeah.
Yeah.
Okay. Yeah, then never mind.
But we got to have multiples of 30 and 45. So what did someone else say? Yep.
Well, 45 minus 30.
Yep, 45 minus 30. That would work. I don't remember the first one, but either way. That's the goal. We're going to write it as 45 minus 30. Now, we're going to figure that out using this formula. Cosine of the first, cosine of the second, plus sine of the first, sine of the second. So we're going to have cosine, cosine, plus sine times sine. And now fill in your angles. First, second, first, second. In our case, 45 and 30. So now, this does require you to know all of those answers. Right? Remember, when we do sines and cosines with 30s and 45s, 1/2 can come up a lot. Square root 3s, square root 2s. But if you don't remember what these all are, at least if you type it in on a calculator and you can recognize the decimal, then we can work with that. So let's start with cosine 45. That's 0.707. What fraction, and it involves a square root, is 0.707? Yeah?
That's square root 2 over 2.
That's square root 2 over 2. I'm not going to check all of them, but I will check this one just to show you. Square root 2 over 2. So 0.707. Okay, so we got that one. Now, cosine of 30. That is 0.866. Does anybody remember what fraction 0.866 is?
Square root 3 over.
Yep, that's your square root 3 over 2.
I knew it.
Those are pretty much the only two choices you have when you do sines and cosines. They could be positive, they could be negative. Root 2 over 2, root 3 over 2. All right, sine of 45. What's that one?
Square root 2 over 2.
Square root of 2 over 2.
It's the same.
The sine and the cosine of 45 are the same.
Oh, that's right. Yeah.
Yep. And sine of 30, 1/2. Okay. So now simplify what we have here. What do you get when you multiply straight across in the first, we'll just say like in this part?
Square root 6 over 2.
Square root 6 over 4. And in the second part?
Square root 2.
Square root 2 over 4. And to add those fractions up, what do you need to have?
Like denominator.
Yeah, we already do. So let's just put it all together. Square root of 6 plus square root of 2 over 4. Let's see if that comes out to 0.9659. So take the square root of 6 plus the square root of 2. That's the top. And now divide it by 4. Plus here. 0.9659. So that's exactly what you get when you type in cosine of 15. But this is the exact answer. Not the most important thing you can do with the sum and difference formulas, but as far as like arithmetic goes, it's probably one of the most basic things we can do to figure out multiples of 15. And there's more than one way to do it. Somebody said, I think 60 minus 45. You could have done that. Any questions on? No. Okay, let's try this. So this is kind of like a proof from the last section, or it's a verify, but it's pretty structured in the way it's going to work. It's not like the kind of verify problems we did in the last section, where sometimes you had to think about, well, should I change the sines and cosines? Should I distribute? What should I do? There's only one thing you can do here. This is a cosine of a difference. So let's use the formula we just learned on the left-hand side and see what happens. Except this time, instead of the angles being a 45 and a 30, it's a pi over 2 and a theta. Those are your angles. All right, so what's the general format for the cosine of a difference?
Cosine, plus
Cosine, yep.
plus sine.
Right. It's always the opposite of what you have right there.
Oh, is it?
When you're doing
Oh, because it's
cosines.
Right.
Right? So the cosine difference formula turns into a sum right there. That's exactly what we did in the last problem. Those symbols are always opposites for cosine. So cosine, cosine, sine, sine. Okay, what's going to go in my first parenthesis?
Pi over 2.
And the second?
Theta.
And then the first? Second. Now, pi over 2 is what in degrees?
30.
90.
That's what I meant.
So, think about that on the unit circle. Where's 90 degrees?
The just the vertical, almost 20.
Yeah, straight up. What's the coordinate for that on a unit circle?
0, 1.
0, 1. And cosine is which value? The x. So based on that coordinate, what's the cosine of 90 degrees? What's the cosine of pi over 2?
0.
0. So this is a 0. And what's 0 times cosine?
0.
So this whole thing basically turns into 0 on the left. Now, let's think about sine. Pi over 2 is 90. What part of the coordinate is your sine? Y. And what's the y value at pi over 2? 1. So this is a 1. So we end up with 1 times sine.
Wait, so is it?
That cancels.
Wait, are both of those become 0?
Because you're multiplying by 0 here. Yep.
I see.
So 0 times anything is 0. So that whole part's 0. And sine of pi over 2 is 1. And 1 times sine is sine. And what's 0 plus sine? Sine. So we just proved that the left-hand side equals 3. Any question on that? Mm-hmm.
How did you get the sine of pi over 2 equals 1?
It's the y value of the coordinate for pi over 2 radians.
Oh, okay. Yeah.
So what we kind of proved here, it's kind of like a horizontal shift. It's not written in the right order, but it does have something to do with the fact that sine and cosine are horizontal shifts of each other. This is kind of like a reflection and a horizontal shift, but we're not really super worried about graphing it right now, just the proof. All right, let's try this one. So another verify. And on the left, we have a cosine difference. Okay, same thing. The next one we're going to do is cosine sum. Okay, let's do one more with the difference. Okay, can somebody set up the left-hand side for me, applying the cosine difference formula to what's written there?
Cosine pi times cosine theta.
Cosine theta. Okay.
Then, it's still sine. Oh, yeah, plus sine pi plus times sine theta.
Plus sine pi sine theta. Okay, so that's just the left-hand side. Right, let's think about pi on the unit circle. Where's pi? To the left. What's the coordinate?
180.
Negative 1, 0. Cosine is your x value. So what is your x value? Negative 1. Yeah. So that turns into negative 1 times cosine. Now sine of pi, sine is your y value. What's your y value?
0.
So that turns into 0. And 0 times sine is 0. So this is gone. And what's negative 1 times cosine? Negative cosine. Which is exactly what it was supposed to be. Any questions on how we applied the cosine difference formula to that?
Alright, do you need to think about the inner circle for each one in order for this to work?
No, as long as you know, if you have these memorized, like if you can tell me the sine of pi, sine of 90, like if you know 90, 180, and 270 off the top of your head, then no. If you don't, then you need to figure it out. All right. There's a couple formulas that are going to come up in what we're going to do next. This is going to come up. And this is going to come up. And I don't think I write them down. Oh, I do. Never mind. So, when we deal with the sine or cosine sum formula, these two things are going to come up. So I'm reminding you of them. We looked at these way back when we started graphing sine and cosine. The first one basically means that cosine is symmetrical over the y-axis. If you graph cosine and mirror image it over the y-axis, it's exactly the same. Because reflecting it horizontally makes no difference. So arithmetic-wise, the idea here is if you have a negative in front of your argument and it's a cosine, you can just get rid of the negative. You don't need it. Here's an example. Take the cosine of negative 25. Take the cosine of positive 25. What's the difference between those two answers? Nothing. Cosine negative 25, cosine positive 25, same thing. Now, with sine, if you have a negative in front of your argument, you can't just get rid of it. But what you can do is you can move the negative to the front. So, based on that, if I had the sine of negative 20, what do you think that would be the same as?
Negative sine.
Yeah. So you can take the negative that's inside your argument to a sine function, and you can put it in front. So just keep these two things in mind. All right. So we want to figure out the cosine sum formula. Well, which formula do we know right now? We know the difference. So let's write what's inside the parentheses as a difference.
Is this the cosine sum formula that we're writing?
It's going to be, yeah.
Yeah.
How can you write alpha plus beta as a difference?
Negative. Oh. Minus beta? You say minus negative?
Alpha what?
It's minus beta.
Well, alpha minus beta isn't equal to alpha plus beta. Alpha minus negative beta.
What does that accomplish, though?
Well, this is your first angle, and this is your second angle. And now you've written it in a format that has a difference, so we can plug these two things in to the formula we already know. And that, once we do that and simplify it, it's going to give us the formula for a sum, and then we won't have to prove it again. So any questions why alpha minus minus beta is the same as alpha plus beta? Okay, let's write down our formula to simplify the right-hand side. Can someone tell me what just kind of like the outline of the formula? You don't have to fill in anything. Just
Cosine times cosine.
cosine times cosine plus sine times sine. Okay. Now I want to fill them all in. What's my first one? Alpha. And my second one? Negative beta. My first one? And my second one. Okay. So we've got some negatives inside those arguments, so we got to fix those negatives.
Wait. Is the top one the formula, or are we finding the formula still?
We're still fine.
Okay.
What happens to this negative in front of beta?
It can just disappear since it's a cosine.
It can just disappear. Because whenever you have a negative inside of a cosine argument, you can just get rid of it. So we end up with cosine alpha times cosine beta. I really don't need parentheses anymore, but when you have a negative inside the argument, if you don't put parentheses, it looks kind of confusing. Then somebody's not sure, like, what's going on. All right. Now, this sine alpha is fine. But what about the negative that's in front of the beta inside the sine?
Take it out.
Take it out and put it where?
In front of the sine.
Yeah, we can put it in front. And that basically is going to turn the plus into a minus. Oh, I don't need parentheses anymore. I'll keep the parentheses in if that makes it look similar. Yeah. And there you go. That is the formula for the cosine of a sum. Almost the same thing as difference. Your cosines are grouped, your sines are grouped, but in between, it's a minus instead of a plus. When you break it up, it's always the opposite of what you put right there for cosine. So that's for the sum. So now you should be able to think about doing something like that. How can you write 75 as a sum, but the two numbers have to be multiples of 30 and 45? Yes, it's 30 plus 45. Now, before we finish it, technically you don't need the sum formula to do this problem. You can do 75 as a difference. Can anybody think of two numbers that you can subtract to get 75?
115 minus 1. 90 minus 15.
Those 15 is not a multiple of 30.
Yeah.
100. No.
So if you did 120, which is a multiple of 30, and 45 is a multiple of 45, you could have done this problem with the difference formula if you recognize this. For some reason, people don't seem to pick up on that as quick as they do on that. So sometimes that's why the sum formula is a little easier. But you can definitely do this as a difference. Okay, so cosine of a sum. Keep your cosines together. Keep your sines together. And what symbol goes between it when we have a plus here? A negative. Okay, what's my first angle? And my second? And there you go. 30, 45. Okay, if you need to, you can type the cosine of 30 in and try to recognize that decimal. I mean, hopefully you kind of start to know those after a little bit. That is important. So the cosine of 30 is how much?
It's pi over 2, right?
Square root 3 over 2.
Oh, it's 45.
How about cosine 45? 2 over 2. The sine of 30?
1.
And the sine of 45?
Square root 2.
So what's your, when you put all that together with a common denominator, what's your final answer?
Square root of 4.
6 over 4. And then
Yes.
2.
Like that.
Why'd you change it to?
Any question on how we got from here to here? It's exactly the same way we got from that step to that step when we did this one. I just did it all in one step this time instead of breaking it out. So a lot of times you end up with square root of 6s, square root of 2s, and 4s in the denominator. Sometimes it's plus square root of 2, sometimes it's minus, but it's usually something like that. Okay.
Oh, wait, so that's a part.
Any questions on that? Okay, so that's how you can do the exact value of cosine and use a sum. All right, now I want to figure out the sine of a sum. And there's something we did earlier that would help us to figure this out. Let's go back to something we verified earlier. In fact, I'll do it on that page. Right here. This is a formula that converts between sines and cosines. And that's what we kind of want to do now. We've got the cosine sum and difference, but we want to convert it to a sine sum and difference. All right, can I use that one to do it? Yeah, I can. So, whatever you have here is what goes right there when you convert it. So we're going to convert this into a cosine. What comes after the minus sign when you convert it to a cosine is whatever you had right there. So what do we have right here in our problem? Alpha plus beta. Just be careful when you write that. It's like that. Okay, any question on why I substituted in alpha plus beta right there?
Sorry.
Any questions on how we got to that step?
Is it always pi over 2, or is it just an example?
Well, no. This is an ident. This is a identity that this always equals this.
So why would it be? Oh, I got you. Because
So-
it's pi over 2 minus beta.
Yeah, it's pi over 2 minus whatever's right here.
If it's adding, you include the alpha and beta.
Yeah, adding would be a different thing. That would be something totally different. We only have a formula to convert between sines and cosines that has a minus in it. Is there one with a plus? Sure. But we don't know it off the top of our head.
So what's the final? Just what's in red? The cosine.
Well, this is going to simplify. We're gonna look at what that simplifies to right now. So there's different ways to simplify it. What would be the easiest? Yeah. Let's think of it like this. So we have pi over 2. Tell me if this would be the same thing. If you thought of it this way.
Yes.
Is that the same thing?
Whoa. I mean, wouldn't it? You just distribute the minus sign.
Yeah. So this is essentially what you have inside here is a pi over 2, a negative alpha, and a negative beta. Break it up, group it any way you want. Pi over 2, a negative alpha, and a negative beta. It's still the same. Now let's solve this with our cosine difference formula. This is going to be your first angle. That's your second angle. What's my cosine difference? What's the kind of the setup for it?
Cosine plus sine.
Cosine, cosine, plus sine, sine. Okay. What's my first angle? Pi over 2 minus alpha. And we know that if we do pi over 2 minus an angle, it turns into something. We'll come back to that. Okay, what's my second angle?
Negative beta.
Negative beta. My first angle?
Pi over 2 minus
And my second angle. Okay, let's start to simplify this. Right here I have the cosine of pi over 2 minus an angle. what does the cosine of pi over 2 minus an angle turn into?
Sine of the angle.
Sine of the angle. So what is this going to be?
Sine. Yeah, sine.
Sine alpha. We proved that if you take the cosine of 90 minus something, it's the same as the sine of something. That was the example 2a that we verified. How about cosine negative beta?
It's just
Cosine beta. Okay. Now, this we didn't quite prove, but it's very similar to this. The cosine of 90 minus an angle is the sine of your angle. What do you think the sine of 90 minus your angle is?
Cosine.
It's the cosine of the angle. We could prove it, we didn't prove it, but it's almost identical to the first one we did prove. And then what about this negative in front of the beta? Bring it to the front. And that is the sine. Sine. Sum, is that the one? Let me just make sure that there are no.
It's the sine sum.
Everything's good except this. We're off with this. Should be a plus. Why? Sine alpha cosine beta plus cosine alpha sine beta. This is just supposed to be a plus. Why? I'm not sure where we went wrong with the plus sign. It's your first angle, your second angle, so the negative just disappears here, and the other negative should go to the front. The only thing I can think of, unless that doesn't turn into what I thought, unless that's a negative in front, and then the other negative cancels it. I'll have to double check it. But that is the correct formula. Just going to put a question mark right there. So one thing you notice, it's a little bit different about the sine of a sum. See, did I do the first step right? Cosine. Yep, that should be a minus. Yeah, everything's right at the second step and the last step. So something in the middle. That's all correct. Well, let's just look at it. So when you have a sum with a sign, the formula has a sum here. So when you're dealing with sines, they're supposed to match. With cosines, they're the opposite. The cosine difference formula uses a plus. The cosine sum formula uses a minus. Not true with sines. The sine of a sum uses a plus. The sine of a difference does use a minus. The other thing you'll notice is the sines and cosines are not grouped. They're mixed. Sine, cosine, cosine, sine. The reason I generally write it in that order is so that I can put first angle, second angle, first angle, second angle. 1, 2, 1, 2. That's how I like to do it. If you write it in the same order on each side, sine, cosine, plus sine, cosine, that's okay, but you're going to have to do 1, 2, and then 2, 1. You're going to have to switch it. So that's the formula for the sine of a sum. And then I think I have difference. That's what we did before. I wish I had my work from like last year. I could just look real quick. But there's your formula for the difference. This matches that. Sine, cosine, cosine, sine. First, second, first, second. So it's more just trying to keep straight which one is which, because they're all kind of similar. Right? All four of them. And I'll do an example with the sine sum because I kind of want to slow down a little, and then we'll split it into two parts. So let's try, we'll do something numeric. Let's find the sine of, let's do 105. Yep. Now, if you can see how to split 105 up as a difference, do it that way. If you can see how to do it as a sum, do it that way. It doesn't matter how you do it.
It has to be multiples of what for this one?
30 and 45. So if you were doing it as a sum, you could do 60 plus 45. Yep. I'll do it that way. Yep.
I was going to give 150 minus 45.
Yep, you could do it that way. And that would do it as a difference. Okay, I'm gonna do it the first way as a sum. Okay, think about the sine sum formula. The first thing is when we split all this up, are we going to have a plus sign or a minus sign in the answer? Right, it's the same. It's always supposed to be the same. Are the sines and cosines grouped together here, or are they mixed? They're mixed. So sine, cosine, cosine, sine. That's the setup. And what's my first angle? Second angle? 60, yeah. And my second angle? 45. Now let's go through it. Okay, what's the sine of 60? Yeah, you gotta get a little quicker at those. So root 3 over 2, what's the cosine of 45?
Root 2 over 2.
Yep, so just that quick is good. What's the cosine of 60?
1/2.
1/2. And the sine of 45? 2 over 2. Okay, what do you get when you put all that together?
Square root 6 plus square root 2 over 4.
We've gotten this one before.
Yeah, because there's the 15s can only have so many different answers. You're either going to have pluses in the numerator, minuses, and for sines and cosines, that's pretty much it. So a lot of root 6 and root 2 in the top. Okay, any question on that? All right, so now, how could you get this? You know enough information to be able to figure that out. Yep.
Split it into sine.
Yeah.
Split into sine.
Right. You could make it as sine divided by cosine.
And then find the either side or difference of both of them.
Yeah. And now you'd have two problems to do. You'd have to do the top one and bottom. Now, there is a better way to figure out something with a tangent, and that'll be the last formula that we do. It doesn't look anything like grouping sines and cosines together with a plus or a minus between them. It's a little different.
Just a little.
So it's the tangent of the first plus tangent of the second. And then in the bottom, it's 1 minus the product of the tangents.
Alright, so is the one on the left the sum and the one on the right the difference? Or
Nope, that's the sum.
okay, alright, that whole thing is the sum.
Yes,
Formula.
that's the tangent of the sum. Now, you've seen, again, this formula looks different, but you've seen the pattern with sines and cosines. Does anybody have a guess what the formula, let's just start with the top, what it would look like for the tangent of a difference?
Tangent alpha minus tangent beta.
Yep, it would be tangent alpha minus tangent beta. And how about the denominator?
1 plus beta. Tangent alpha minus tangent beta.
Say the bottom again?
Would it be plus instead of minus?
Yeah, just plus instead of minus. So at least the idea of the pattern is pretty similar in that all you have to do is change your pluses to minuses and your minuses to plus. That's pretty much exactly how the other identities worked. But it's a little bit more complicated, but you can kind of see it has a fraction in it. And that's because if you were going to figure out tangent, it would be sine over cosine. Tomorrow we might look at one of these and see why this is the formula based off the sines and cosines that we learned today. The tangent ones, I'm going to tell you, you don't have to worry as much about those for this test. I'm putting them up there because if you're going to study the sum and difference formulas, it's good to have them all in the same spot. So if you keep your notebook next year and take calculus, you got everything if you wanted to look it up all in the same spot. But we're going to really focus on sines and cosines in this class. Okay, so those are what we call sum and difference. Tomorrow we'll pick up with the tangent sum and difference. We'll look a little bit more at it. And then the last two groups of identity we're going to look at are what we call double angle. And there's half angle, but I might have taken those out. So double angle, we'll focus on those, and then we'll finish up with half angle. Okay, let me just adjust that a little bit. Okay, I think Alright, we'll try those. Okay, so 2 through 5, 9, 10, 31A, and 37.